Imagine trying to read a story that's 4 billion years old. A story with no words, no pages, just clues written in bone, stone, and even our own DNA. So how in the world do we piece together the incredible history of life on Earth? Well, let's dive in and see how scientists became master detectives of the past. That's the big question, right? It really is like being a detective at the scene of the biggest mystery ever. We've got clues scattered all over the place across millions of years, and our job is to put them all together. And you know, our investigation, it doesn't start in the distant past. It actually starts at the very beginning of an individual life.
Okay, just take a look at this. On the screen, we've got a fish, a salamander, a tortoise, a chick, and even a human. And in their earliest embryonic stages, wow, they are almost impossible to tell apart. I mean, they look incredibly alike. So what is going on here? What does this tell us?
Well, this leads us directly to our first major line of evidence, these amazing echoes of our ancestors that we can see before we're even born. We're talking about a field called comparative embryology, and believe me, it is a fascinating window into our deep shared history.
So what does this fancy term actually mean? Well, it's pretty simple. Scientists are comparing these very early stages of development across all sorts of different species, and they're looking for those similarities we just saw. And it turns out, those patterns, they tell a really profound story. And here's the key takeaway. These similarities are absolutely not a coincidence. They are really strong evidence that all of these different animals, from a fish all the way to a human, we all share a common ancestor. It's like we're all working from a very similar developmental blueprint, because that blueprint was handed down from an ancestor we all have in common.
And this reveals a really powerful rule of thumb. The more closely related two species are, the longer their embryos stay looking alike as they develop. So, for example, a rabbit embryo and a human embryo will look similar for much longer than, say, a fish embryo and a human embryo. It's a brilliant way to see just how close we are on the family tree of life.
All right, so we've seen the echoes of the past in the beginning of life. Now let's jump in our time machine and go way, way back to look at the hard evidence. We're about to dig into the Earth's very own library, the incredible stories written in stone.
Now, the fossil record is pretty much what it sounds like. It's a history book made of fossils. But these aren't just a bunch of old bones. They're the actual preserved remains or even just imprints of ancient life. Every single fossil is like a snapshot from a different time. And when you piece them all together, you get this amazing timeline that shows us how life has changed, bit by bit, over millions of years.
So this is a great question to ask ourselves. We've looked at evidence from how life begins and from ancient remains. But, evolution isn't just something that happened a long time ago. There are clues carried around inside the bodies of living animals right now. Clues that are basically hiding in plain sight.
And that brings us to one of the most interesting, almost spooky lines of evidence. We could call them ghostly evolutionary leftovers. These are parts of an animal's body that don't seem to do anything anymore, like little whispers of a life their ancestors used to live. The scientific term for them is vestigial structures. So a vestigial structure is any part of the body, an organ, a bone, anything, that's lost its original job over the course of evolution. A good way to think about it is like leftover code on your phone from an old operating system. The code is still there, but it doesn't actually do anything anymore.
And one of the most famous examples of this is found deep inside the body of a whale. Check this out. Tiny, completely unused pelvis and leg bones. Now, you got to ask yourself, why would an animal that swims in the ocean have leg bones? It makes zero sense. Until you look at its history. And the answer is just amazing. These bones are remnants. They're leftovers from a time when the ancestors of modern whales were actually land animals that walked on 4 legs. They don't need the legs for walking anymore, obviously, but the genetic instructions to build them haven't totally vanished. They are literally fossils inside a living animal. So cool.
Okay, so we've got all this incredible evidence. Embryos, fossils, those weird ghost structures. But for this whole story to really make sense, we need to know when everything happened. I mean, how on earth do scientists put an actual date on a fossil that's millions of years old? Well, it turns out they have some incredibly clever ways to read time itself. So there are 2 main ways to do this. First, you've got relative dating. This is kind of like looking at a stack of newspapers. You know for a fact that the papers on the bottom of the pile are older than the ones on top, right? But you don't know the exact date they were printed. Then you have radiometric dating. This is like looking at the actual date printed on the newspaper. It gives you a precise age in years. Let's zoom in on the most famous method of radiometric dating, good old carbon-14. See, while any organism is alive, it's constantly taking in carbon-14 from the environment. But the second it dies, that stops. And that's the moment an invisible atomic clock starts ticking. Okay, so let's break down how this atomic clock works. Step 1, while something's alive, it has a steady amount of carbon-14 in its system. Step 2, after it dies, it stops taking in new carbon-14, and the stuff it already has starts to decay at a super predictable rate. So for step 3, scientists just measure how much carbon-14 is left. And finally, because they know exactly how fast it decays, they can calculate how long ago that organism died. It's ingenious.
In this number right here, this is the secret sauce that makes it all work. The half-life of carbon-14 is 5,730 years. What that means is, if you start with, say, a pound of carbon-14, in exactly 5,730 years, you'll have half a pound left. Wait another 5,730 years, you'll have a quarter pound. Because this rate never, ever changes, it gives us a super reliable clock for dating things up to about 50,000 years old.
So, let's put it all together. What's the verdict? We've got developmental echoes in embryos, all pointing to a shared blueprint. We have a massive storybook written in stone, the fossil record, that shows a clear history of change over time. And we have these evolutionary ghosts inside living animals, reminding them where they came from. 3 totally different types of evidence, and they all point to the exact same powerful conclusion, that life on Earth shares a common ancestry and has been changing, evolving, for a very, very long time.
You know, the evidence we've just looked at pieces together this incredible history of where we all came from. It's a story of connection, of change, and of almost unimaginable amounts of time. But it also makes you wonder, doesn't it? This process hasn't stopped. So if this is the story of our past, what story will our biology tell millions of years in the future? What clues will we leave behind?